Okay, some of these videos are running a little bit longer than I, I want them to keep it about 5 or 6 minutes, but I get carried away. But we'll just have less of them. Anyway, here's a parallel plate. Well, the difference between two equal potential surfaces, and for our purposes in this course, we're going to always have E be a constant as it's flowing through. In other words, E stays the same as it flows through equal potential surfaces. Okay, E will stay the E will stay the same. Now the voltage is going to change because this is going to be a higher voltage at this blue surface than at this negative. So in other words, if I take the change in the voltage, if I take negative 12, let's say this is 20 volts and this is 10 volts. Okay, 20, 10. All right, I wish I could write on it. I wish this was like a little iPad or something like that. Sorry, I thought I turned it off, but I guess not. Anyway, so then if this was like 20 and this is 10, let's say this is 18 and this is 12. So if I take 12 minus 18, which would actually be the change in voltage, that would be a negative 6 volts, divided by this positive distance here, then the negative of that negative would give me the positive E field going from emanating from the positive side to the negative side. But the E field is going to stay the same. And this is where we get that the E field, is times the distance. E field times the distance equals the equal potential, equals the equal potential surface. In other words, the voltage is the same here throughout this area, and the voltage throughout this area is the same over here. This could be, like I said, this could be 18 volts throughout here, and this could be 12 throughout here. All right. So the plates of the capacitor are separated by a distance of 0.3. So the entire capacitor is separated by a distance of 0.032 meters. That's small enough so that the electric field is going to stay the same. The potential difference between B and A, so if I take VB minus VA, that'll equal delta V is equal to 64 volts. Between the two equal potential surfaces shown in the color, there's a potential difference of 3 volts. D-E. Find the spacing between these two surfaces. All right, we're going to do that. We're going to do that because this is a good problem to do, and then we can jump into, what's the next slide? Oh, I don't want you. Okay, then we can jump into capacitors. Okay, well, I guess you could follow the slide anyway. So, all right, so here we go. 0.032, negative 64, negative 3. All right, so here's what we had. You got E field going through, and then we've got this little plate here. E field's going through it, and we got this one here. We need to find the distance between those two plates. All right, you can go back and look at a better picture than I can draw. All right. We just have to know that this E field is the same all the way through. Okay, now the distance between these two plates, D, is equal to 0.0032 meters. All right, really close together. So the E field is going to be uniform throughout. All right. Okay, and I know that negative 64 is equal to delta V. Okay, so negative 64 is equal to delta V. So let's just plug in, and so I know that the E field is equal to the opposite of negative 64 over 0.0032. Is it 0.00 or just 0.3? 0.032. Gosh dang it. Too much caffeine. All right. Oh, the good thing is you didn't see me write that. So let's just do it again. Changes negative 64 volts. Okay. E field then would equal, and this is 0.032 meters, is equal to negative 64 over 0.032 meters. It's the negative of, so it comes out to be positive. Oh, it looks like, look what we have here. We've got 64 times 10 to the 0 divided by 32 times 10 to the negative 3. Volts per meter. Whoa, volts per meter. That's a new one. Remember, so now E field can either be volts per meter or newtons per coulomb. Whoa. And how do I get a vector out of a scalar? Well, it's because they're dividing by the displacement, and this is the way the math works. You know, I did this because I've got 2 times 10 to the negative, if I've got 0 minus negative 3, that becomes positive 3. So I've got 10.0 times 10 to the positive 3 volts per meter. Or newtons per coulomb. That's my E field. 2,000 newtons per coulomb or volts per meter. Okay, so now they want me to find out what the potential is between these two distances here. Well, I know then that E is equal to the negative change in voltage between, what were they saying? Oh, they want to find the space between A and B. Okay, so we got that. Over the change in S. This time, change in S is between the difference between B and A. Okay, the delta S is the difference between B and A. So I've got 2,000 is equal to negative of the negative 3.0 divided by delta S. Okay? So delta S is equal to 3.0 of B to A, 3.0 over 2,000, which is 3.0 times 10 to the 0 over 2.0 times 10 to the third. And so I wind up with that change in S is equal to 1.5 times 10 to the negative 3 meters. We don't need no stinking calculators. We can just use exponents. Be interesting to see if I'm right after all that. Yeah, look at, I rule. See, they kind of drop and they don't show you why. Now we're going to talk about capacitors and dielectrics. This is at the end of this. Now that we're done with this one, now we're getting into Monday's lecture, big time. Okay, maybe even Wednesdays. This could be we're getting into Mondays and Wednesdays lecture. Okay, so as a matter of fact, I think I'll quit here because I think we'll have enough. In other words, I'm not going to go on to capacitors. I'm going to look at some of your homework problems that we have. Oh, what's going on here? Over. Yeah, let's just look at some homework problems.